Ever wondered how AI deciphers the tangled web of connections in real-world data? Like mapping how movies, actors, and directors intersect, or how proteins interact in the human body. It's not as simple as it sounds. Traditional models struggle with heterogeneous graphs, networks where nodes, like people, movies, or proteins, have different types and relationships. Some connections are straightforward, like actors working together, but others are complex, like a movie influencing a director's style. This mix of homophily, similar nodes connecting, and heterophily, different nodes connecting, has long been a challenge for AI. But here's the twist. Researchers aren't just solving this problem, they're building a model that adapts to it. Enter AHGNN, or Adaptive Heterogeneous Graph Neural Networks. Think of it as an AI that's not just smart, but street smart. It adjusts its approach based on the data it's given. So how does it work? Let's break it down. AHGNN tackles 3 key parameters. L1, how far information spreads in the network. L2, how labels propagate. Alpha, a knob for adjusting how different node types interact. But here's the kicker, you don't need to perfect these settings. Even if you fiddle with them a bit, AHGNN still delivers solid results. Why? Because it's designed to be forgiving. Real-world data is messy. Some datasets are noisy, some are sparse, and others have weird rules. AHGNN doesn't panic, it rolls with the punches. The magic lies in its design. Imagine a traffic system that dynamically reroutes cars based on real-time conditions. AHGNN does something similar with data. It uses adaptive convolution to adjust how information flows through the graph, prioritizing the most relevant connections. Then there's the Coarse-to-Fine Semantic Fusion module, which acts like a spotlight, amplifying meaningful patterns while ignoring the noise. For example, in a movie database, it might focus on actor-movie links while sidelining longer, less relevant chains like actor-director-writer. The results? AHGNN isn't just fast, it's efficient. In experiments, it used less than 1/10 the memory of some competing models while maintaining high accuracy. That's a game changer for handling massive datasets without crashing your computer. And the visualizations? They're like watching the AI's thought process in action, dynamically shifting focus across the graph as it learns. So why does this matter? AHGNN isn't just another AI model. It's a flexible tool for navigating the complexity of real-world data. Whether you're analyzing social networks, medical records, or supply chains, this adaptability could revolutionize how we tackle messy, unpredictable information. Let's dive deeper. At its core, AHGNN leverages metapaths, specific routes through the graph that act as viewpoints to explore relationships. For instance, in a scientific network, a metapath might be author right arrow paper right arrow author, or author right arrow paper right arrow conference. Each reveals unique patterns. But how does the model process all these paths effectively? The first stage, adaptive heterogeneous convolution, creates messages that travel along each metapath. Think of it like a rumor spreading through a social network. Each step passes along information. But here's the innovation. The model adapts to the graph's heterophily, a term for when nodes connect to dissimilar ones. In some parts of the graph, similar nodes cluster together, homophily, while in others, connections are more varied. AHGNN adjusts its message passing to handle both scenarios, ensuring it doesn't miss critical patterns. But with so many metapaths, not all are equally useful. That's where Coarse-to-Fine Semantic Fusion comes in. This module acts as a filter, starting with a coarse scan to identify the most relevant connections, then zooming in for detail. It uses attention mechanisms to prioritize information, assigning weights to each metapath based on task relevance. For example, predicting research trends might prioritize conference-related paths. The model also employs KL divergence to ensure different parts of the network learn unique perspectives, avoiding redundancy. What makes AHGNN special is its efficiency. By pre-computing messages and adapting to graph structure, it handles large, complex datasets without getting bogged down. And its power lies in blending multiple metapaths intelligently, capturing nuanced relationships that simpler methods miss. So the next time you see a network of connections, whether in science, entertainment, or biology, remember, tools like AHGNN are decoding the stories hidden in those links. Thanks for watching. Stay curious, and let's keep exploring the science behind the data.